Hello ladies and gents, welcome to our next lecture. We're going to be going into the derivation of the equation for calculating the force in a bolt group loaded in plane. So as we get into the example, here you'll see a bolt group, 12 bolts on the right hand side with a single force F subscript U applied to the bolt group, and this is acting at some location EX and EY relative to a center of rotation. So that's measured from those two red dots to each other. And now we want to calculate what is the force in the most stressed bolt. And you'll see on the left hand side here the equation given in the Green Book, the South African Institute of Steel Construction Green Book, for the design of bolt groups. So what we're going to just find out is how to get to that equation. What's the basis of it? We can use it exactly as it's shown there, but we're going to just see where do those terms come from and how do we apply them. So firstly, let's go now back to our design on the right hand side, and what we're going to have now is we're going to break this force up into vertical component, a horizontal component, so that F subscript U then becomes FUX and FUY, and then though that vertical and horizontal component we can just transfer to be at the center, and then that force gets divided up equally amongst the bolts in either direction. So that's quite easy. But then also we have a moment now acting at the center, M subscript U. And we need to now convert that one force, Fu, into two forces in a moment acting at the center there. And we're going to start running through now how to go about this calculation of the force in the most stressed bolt, FUJ. So here you'll see I have taken the force FUJ, broken up into horizontal components just by dividing the force by the number of bolts, the vertical component, and then the two components horizontally and vertically due to the moment, and then the moment is the vertical component times x distance and horizontal component times y distance, so force times distance. Now we need to find out how is that moment to split up amongst the bolts. What is the force in bolt FUJ, or in bolt J, due to this force? So let's start going through that. So if we take the moment mu, that will be due to the force contributions of all individual bolts, a perpendicular force acting at a perpendicular distance, Li times Fi, but the distance from the center of rotation to the bolt is just its x and y components by Pythagoras. So we end up, if there are a number of bolts, 4n bolts, we end up with a term that would look something like that. That would give us our total moment contribution. These are just forces times distance. So let's see what it would look like on this diagram. So here you can see the forces due to the moment, the vertical and horizontal forces in each bolt. And so if we have a look at bolt J here, there's some force due to the moment Fj, and then it is a distance Lj from the center of rotation, where that is then Lj is x squared plus y squared square rooted. So coming back now to our derivation, let's take this through and start playing with this to get the moment as a function of Fj. So with Fj being the force in the bolt, any other force, F subscript I, would just be proportional to that, because the further a bolt is away from the center of rotation, the higher the force is. Kind of like the distance a fiber away is from the neutral axis. As you get further away from the neutral axis, the stress increases. So here we have the some bolt Fi, at a distance Li, it would just be ratioed relative to the force J. So we end up with a term like this. So now we're going to manipulate the formula for the moment about the center of rotation mu and get it in terms of x's and y's. And the reason we're using x's and y's simply because they're very easy to work with. Normally in a steel connection, we have all the x and y coordinates quite easily. Working out diagonal distances is more difficult, so this makes our calculations simpler. So here we have the moment in terms of force F, subscript J. So now that we can take this further and manipulate this into a form that we can use. But also what's useful to define now is a polar moment of inertia, where the polar moment of inertia describes the distance of all the bolts from the center of rotation. So there is the polar moment of rotation that we can then use to describe the position of all the bolts together. And normally we'll use this form, just the distance in x and y, but if we know the perpendicular distances, we could also use that. Now I'm going to further manipulate the equation to get it into the format of what's shown above. So here you'll see with a bit more manipulation converted Fj, the force due to the moment only, into that form as shown, and that has a horizontal and a vertical component to it. And then if we now add to it the horizontal and vertical components due to the bolts above, so due to this diagram here, if we include that in our analysis, then we end up with our total force Fuj. And then just to make clear what I have been calculating up until now, is just Fj is just the moment component. And now, oops, sorry, I drew that in the wrong place. Let me shift that. Fj is the top one. Now, once we have all of that, then we can now finalize our analysis and go ahead and get it into the form as below, that form there. And this is then the governing equation. So this is to determine the force in bolt J due to a horizontal force X, a vertical force Y, and then a moment about the center of rotation. And that is then the derivation and how we got to that equation. Thank you.